NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will find the vertex and the axis of symmetry for a quadratic function, given in general form f of x equals ax squared plus bx plus c. We will first state the theorem, then we will prove it by completing the square, and finally we will visualize minimum and maximum cases on a graph. Theorem: for f of x equals ax squared plus bx plus c. 1. The vertex is the point A with coordinates open parenthesis negative b over 2a, comma, for a c minus b squared over 4a, close parenthesis. 2. The axis of symmetry is the vertical line x equals negative b over 2a. Proof by completing the square. Step 1. Start with f of x equals ax squared plus bx plus c. Factor out from the quadratic and linear terms. Step 2. To complete the square inside the parentheses, add and subtract the term b squared over 4 squared. Step 3. The first 3 terms now form a perfect square. Rewrite them as open parenthesis, x plus b over 2a, close parenthesis squared. The remaining constant inside the brackets is, for ac minus b squared over 4 squared. Step 4. Distribute a to arrive at the vertex form. This yields f of x equals a times open parenthesis x plus b over 2 a close parenthesis squared plus open parenthesis 4 ac minus b squared close parenthesis over 4a. From the vertex form, the vertex is at x equals negative b over 2a and y equals 4 ac minus b squared over 4a. The axis of symmetry is the vertical line x equals negative b over 2a. Now, 2 cases. If it is greater than 0, the parabola opens upward, and the vertex gives the minimum value. Specifically, f of x is greater than or equal to for ac minus b squared over 4a. If it is less than 0, the parabola opens downward, and the vertex gives the maximum value. Specifically, in this lesson, we will prove an important optimization result. Among all rectangles with a fixed perimeter, the square has the maximum area. We consider a rectangle with length x and width y. The perimeter is fixed and equals 2 times in parentheses x plus y. The area is x times y. We seek to maximize the area subject to that fixed perimeter. Step 1. Write the key formulas. Perimeter equals 2 times x plus y. Area equals x times y. Step 2. Since the perimeter is fixed, we can express y in terms of p and x. From p equals 2 times x plus y, we get y equals p over 2 minus x. Step 3. Substitute this expression into the area. The area becomes s of x equals x times in parentheses p over 2 minus x, which simplifies to s equals p over 2 times x minus x squared. This is a downward opening parabola in x. Before we find the exact maximum, let's build intuition with a visual. We'll fix the perimeter to p equals 8 units for demonstration. As x changes, y will update to keep the perimeter constant. Watch how the rectangle's area behaves as the shape changes. Now, to find the exact maximum, observe that s of x equals p over 2 times x minus x squared is a concave down quadratic in x. The maximum occurs at the vertex given by x equals negative b over 2a, here at equals negative 1, and b equals p over 2, so x star equals p over 4. For our demo, with p equals 8, that is x equals 2 units. The vertex tells us x star equals p over 4. Then y star equals p over 2 minus x star, which is also p over 4. So the rectangle with the largest area has equal sides. It is a square. The maximum area equals p squared over 16. Now, watch the demo rectangle move to x equals 2, y equals 2, a perfect square for p equals 8. Summary: with a fixed perimeter, the area function in terms of x is a concave down parabola, achieving its maximum at x equals p over 4. This yields y equals p over 4, so the optimal rectangle is a square, and the maximum area is p squared over 16. In this optimization problem, we want the maximum area for a rectangle next to a C using a 120-meter fence. Only 3 sides need fencing, the bottom and the 2 vertical sides. Let's build an intuitive diagram, name our variables, and write the perimeter and area equations step by step. Let x be the length parallel to the C, and w be the width. Only the bottom and the two sides are fenced. So the fence length is x plus 2w equals 120 meters. We solve for w in terms of x. 2w equals 120 minus x, so w equals 60 minus 1/2 x. The area of a rectangle is length times width. So A equals x times w. Substituting w gives A equals x times the quantity 60 minus x over 2. Expand to get A equals negative 1/2 x squared plus 60x. To find the maximum, we complete the square. Factor negative 1/2. A equals negative 1/2 times the quantity x squared minus 120x. Add and subtract 3600 inside. A equals negative 1/2 times the quantity x squared minus 120x plus 3600 minus 3600. That becomes A equals negative 1/2 times the quantity x minus 60 squared plus 1800. Because the coefficient of x squared is negative, this parabola opens down, so its vertex gives the maximum. Let's graph A versus x to see it. The vertex occurs at x equals 60 with maximum area 1,800 square meters. At the maximum, x equals 60 meters. Compute w. W equals 60 minus 1/2 times 60, which is 30 meters. Check the fence length x plus 2w equals 60 plus 2 times 30 equals 120. And the area, 60 times 30 equals 1,800 square meters. In this example, we will find the maximum and minimum values of the function f of x equals the cube root of negative x squared plus 2x plus 4, using a clean algebraic algorithm based on the discriminate condition. Here is the example. Calculate the minimum and maximum values of the function f of x equals the cube root of negative x squared plus 2x plus 4. Step 1. Determine the domain. Because we have a cube root, which is an odd index, the inside expression can take any real value. Therefore, the domain of f is all real numbers. Step 2. Remove the cube root by cubing both sides. Then f cubed of x equals negative x squared plus 2x plus 4. Move all terms to one side to create a quadratic in x with a parameter f cubed of x. Step 3. For real x solutions to exist in the quadratic, we need the discriminate to be greater than or equal to 0. Here, at equals 1, b equals negative 2, and c equals negative 4 plus f cubed of x. Using the half discriminate formula delta prime equals b over 2 quantity squared minus ac, we get 1 minus 1 times the quantity negative 4 plus f cubed of x. That simplifies to 5 minus f cubed of x greater than or equal to 0. Step 4. Solve the inequality. From 5 minus f cubed of x greater than or equal to 0, we get f cubed of x less than or equal to 5. Taking the real cube root on both sides yields f of x less than or equal to the cube root of 5. This gives the upper bound of the function. There is no lower bound because the inside, negative x squared plus 2x plus 4, can go to negative infinity as x goes to positive or negative infinity. So f of x goes down without bound. In this lesson, we will find the minimum and maximum values of the function f of x equals the square root of negative x squared plus x plus 1. We will follow a clean 5-step algorithm to make the reasoning airtight. Step 1. Determine the domain. For an even root to be defined, the radicand must be greater than or equal to 0. So we set negative x squared plus x plus 1 greater than or equal to 0. To understand this set, we first find the roots of the quadratic negative x squared plus x plus 1 equals 0 using the quadratic formula. The discriminate is 1 squared minus 4 times negative 1 times 1, which is 5. Therefore, the roots are 1 plus square root 5 over 2 and 1 minus square root 5 over 2. Since the quadratic opens downward, the radicand is non-negative between these two roots. That closed interval is the domain. Step 2. From a quadratic in x, square both sides to remove the square root. Then move all terms to one side to get a standard quadratic in x with a parameter f of x. Step 3. Require that real x exist. For a quadratic in x to have real solutions, the discriminate must be greater than or equal to 0. Here, at equals 1, b equals negative 1, and c equals negative 1 plus f squared of x. The discriminant is 1 minus 4 times 1 times negative 1 plus f squared, which simplifies to 5 minus 4f squared of x, and that must be at least 0. Step 4. Solve the inequality for f of x. Move terms to get 4f squared less than or equal to 5. So f squared is less than or equal to 5 over 4. Taking square roots gives the absolute value of f less than or equal to square root 5 over 2. Initially, that looks like f between negative square root 5 over 2 and positive square root 5 over 2. Step 5. Refine with non-negativity. Because f of x is a square root, it can never be negative. So the final range is 0 less than or equal to f of x less than or equal to square root 5 over 2. That means the minimum value is 0, and the maximum value is square root 5 over 2. In this lesson, we will find the minimum and maximum values of a quartic function by grouping, substitution, and completing the square. Here is the problem. Find the minimum and maximum of y equals parentheses x minus 5 times x minus 1 times x minus 6 times x minus 2 close parentheses plus 9. Strategy. We will pair the factors so that each pair expands to the same middle term x squared minus 7x. The pairs are left parenthesis x minus 5, x minus 2 right parenthesis, and left parenthesis x minus 1, x minus 6 right parenthesis, because negative 5 plus negative 2 equals negative 7, and negative 1 plus negative 6 also equals negative 7. Expand each pair. Now set u equals x squared minus 7x. This turns our expression into a clean quadratic in u. Multiply to get u squared plus 16u plus 60, then add 9. That is u squared plus 16, u plus 69. Complete the square. Write 69 as 64 plus 5. Then u squared plus 16u plus 64 is left parenthesis u plus 8 right parenthesis squared. So y equals left parenthesis u plus 8 right parenthesis squared plus 5. A square is always non-negative. Therefore y is at least 5, with a minimum of 5. The square becomes 0 when x squared minus 7x plus 8 equals 0. Use the quadratic formula to find the x values. X equals 1/2 of 7 plus or minus the square root of 17. Let us visualize the function to confirm our result. We draw axes for x from negative 1 to 8 and y from 0 to 80. Now we plot the function y equals parentheses x minus 5 times x minus 1 times x minus 6 times x minus 2 close parentheses plus 9. Draw a dashed line at y equals 5. Finally, mark the two minimum points at x equals 1/2 of 7 minus the square root of 17 and 1/2 of 7 plus the square root of 17. Both have y equal to 5. In this lesson, we will find the maximum height of a rocket launched upward. The height as a function of time is given by h of t equals negative 16t squared plus 144t. Our goal is to find the highest point on this parabola. We'll also build an intuitive graph to see why the vertex gives us the maximum height. Let's draw a time versus height graph. Then, we'll plot h of t equals negative 16t squared plus 144t. We'll also fly a small rocket along the curve, so we can watch it climb to its peak and then come down. Step 1. Find the time when the height is maximum, the vertex time. For a quadratic, a t squared plus bt plus c. The time at the vertex is negative b over 2a. In our function, a equals negative 16 and b equals 144. Substitute these values. Compute to get t sub s equals 4.5 seconds. On the graph, the vertex occurs at t equals 4.5 seconds. Let's mark it visually with dashed guides. This is the highest point of the parabola. Step 2. Compute the maximum height by evaluating h at t equals 4.5. Substitute t equals 4.5. Square 4.5 to get 20.25. Multiply negative 16 times 20.25 equals negative 324, and 144 times 4.5 equals 648. Finally, add them to get the maximum height of 324 meters. So, the rocket reaches a maximum height of 324 meters at 4.5 seconds. Let's place a clean label on the graph to summarize. This matches the vertex. Let's model a parabola from its intercepts and graph it cleanly. We are told the graph passes through the point 0, 2, and it crosses the x-axis at -1 and at +2. Our goal is to find the quadratic function, and then sketch it, emphasizing the vertex and axis of symmetry. Step 1. Use the y-intercept to find c, because the point 0, 2 lies on the graph. When x equals 0, the output is 2. That means c equals 2. So we reduce the function to ax squared plus bx plus 2. Step 2. Use the x-intercepts to create two equations in a and b. Substituting -1, 0 gives 0 equals a times 1 minus b plus 2, so a minus b equals -2. Substituting 2, 0 gives 0 equals for a plus 2b plus 2. That simplifies to 2 a plus b equals -1. Step 3. Solve the system. Add the equations a minus b equals -2 and 2a plus b equals -1. The b terms cancel, giving 3a equals -3, so a equals -1. Substitute back to get b equals 1. The quadratic is f of x equals -x squared plus x plus 2. Step 4. Find the vertex using x equals -b over 2a, with it equals -1, and b equals 1. X vertex equals +1/2. Substitute x equals 1/2 to get y equals -1/4 plus 1/2 plus 2, which simplifies to 9/4 or 2.25. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.